All right, here we go. What do we talk about this chapter?
Gas.
Okay, yeah.
Gas laws.
Talk about gases, gas laws. And we talked about the kinetic molecular theory, correct? All right, and we talked about quite often in various different forms how an ideal gas is really just a hypothetical concept, and that it's not always the case. But under certain situations, we can use nice approximations because some gases act ideally under certain conditions. Do you guys remember what those conditions were?
High temperatures and low pressures.
Okay? And there was a reason why it was those conditions that were important, and it had something to do with the kinetic molecular theory. Do you remember how that related to the kinetic molecular theory? Distance between us?
Or the distance is so great that their like mass is zero.
Okay, I see what you're saying.
When it's at ideal conditions, most of it's open space.
Yeah, okay, yeah. So most of it's open space, so the volume of the gas particle itself does not play an important part in the overall volume.
And at high temperatures, they're moving so fast, they don't interact with each other very much. But at low temperature, it's moving slower, and so they attract each other more.
So really there were two things that we were assuming. Here are those two assumptions that we were making. The first assumption is that gas particles have no volume. Second assumption is that there are no particle interactions. Those are our two assumptions that allowed us to use all of these gas laws, and that really all gases kind of acted ideally or the same under these situations. Now, in order for the assumption to be true, what did the conditions have to be for this one? What was the conditions that related to gas particles having no volume? And then what had to be true for the particles to not interact with each other? Okay? Well, what we know is that this isn't 100% correct. We do know that particles do interact. It is correct that under high temperatures, they interact so small, or they barely interact at all, that we can consider it to be an aqueous flow. And we do know that gas particles have a volume. And we do know that gas particles for like hydrogen and helium and all those guys actually have slightly different particle volume, correct? Okay? But the difference in the volume of a helium nucleus and the volume of, or a helium atom and a hydrogen atom is very, very small compared to the great distances that gases can occupy, or the great spaces that gases can occupy. So it's like adding 0.0000001 liters to 1. What does that really just round to? 1. It's a negligible addition. Okay? So what we are going to talk about today is Mr. Johannes. I think that's how you say his name. I like to say Johannes. van der Waals. He was the first person to do some important work in the area of how to correct for situations when we're not in ideal conditions. Okay, so obviously it would be the opposite, or non-ideal conditions would be high pressure, low temperatures. Okay? Why would low temperatures cause a problem?
It's the molecules that interact with each other.
Now, why does temperature have anything to do with how they interact? Wouldn't like charge and things like that be what you would be thinking about?
Slow down.
As they slow down, okay?
When they slow down, so it's like two magnets, right? When you raise magnets, you don't feel any pull, but if you move slowly, it's hard to keep.
So they're still attracted to each other,
Yeah.
but it's so negligible because they're moving so fast.
Yeah.
Okay? How about why would high temperatures make this assumption not true?
High pressure.
Yeah, no, I said. Oh, sorry, high pressure.
When they're, what was it you said, when they're tightly packed, the volume matters more.
Because remember how I said, like, let's say 20 liters is the volume that the gas occupies. Okay? Let's say I've got a hydrogen in 20 and helium in 20 liters. Okay? Well, remember, most of gas is open space. Okay? Well, the hydrogen atoms and the helium atoms do occupy some of the 20 liters. So technically, hydrogen and helium don't have a full 20 liters of volume that they can take up. It's actually a little bit less than that because their own volume themselves take up some of that space. Okay? But if we're talking about a situation under very low pressures, the actual volume of each of these individual particles is very small. Like, so I take 20 liters and add the volume of the particle itself, and it's still basically what? 20. Let's say we compress it down a lot. Now that number becomes important. I might have really went to the extreme here. I don't know if it's that far off. But if we start pressurizing it, we're starting to remove and change some of the overall volume without impacting the volume of the particle itself. And so those numbers are going to get closer to each other, and now they're important. Okay? So, let's figure out what Mr. Johannes did. I'm trying to think here if I have much of a PowerPoint or if it's just kind of, nope, no PowerPoint. Not funny. I hate when students act like this. It makes my day awful. I mean, I'm not saying it's not normal. It's just makes what I do.
We can be really loud and not obey.
Honestly, I'd almost take that.
You heard a camera. Kramer wants to not behave.
So freshman class is not your favorite?
No.
They're not your favorite. You heard that too, yeah.
Alright, fine.
I actually went on Schoology and watched this video.
How many of them?
2 or 3. I skipped it. I skipped and
Just to like relearn or just to see what
a
it was
little bit
like?
of review for the homework just to make sure I was doing it right. I didn't, but I thought I did.
Did you figure out what you were doing wrong by watching the video?
No, I did it wrong in the homework.
I know, but did watching the video help you?
It helped me remember the other stuff, yeah.
Okay.
I did the quiz coming up, so it's reviewing.
You
But I-
guys stop now.
I went and watched a lot of the funny moments. There were a few.
In this class?
Not a lot yet, but there's some funny ones.
Alright, so let's open up our books here. This is all theoretical jazz, so let's, and not necessarily theoretical, but like very conceptual. We're going to be on page 214, 215. Alright? So we have an ideal gas law that we use to really But remember, the ideal gas law only works effectively when we're at low pressures and high temperatures. So really, we need a new equation if we were to do gas calculations at high pressures and low temperatures. Okay, so Mr. Johannes van der Waals was the first to do work in this area, and he realized that real gases do take up a volume. They have very finite volumes. Okay, so therefore he had to make some sort of adjustment, per se, to account for this. Right? So what he noticed is that if we assume that the gas particles take up no volume themselves, then the volume of the container is simply just the volume of the gas. Okay? However, since gas particles actually do take up some of this container volume, we would need to make a correction. The volume available to the given particle of a real gas is going to be less than the volume of the container. Okay, everyone hear what I said? So the container is what? Let's say 20 liters. Okay, well, the actual atom's particle size, or its volume, is going to take up some of that 20 liters. So when we were doing our math, we just plug in whatever the container volume is, correct? Usually? All right? Well, it's always going to be a little bit less because the particle takes up some of that volume. Does that make sense? So what he's saying is it's not actually 20. It's slightly less than 20. Okay, great, Mr. Johannes. How do we figure out what that number actually needs to be? Here's what he did. He figured out that the volume of the container needed to be corrected. So he had some sort of correction factor. Let's see, I should probably just read right out of the book here, instead of trying to abbreviate all this. All right, let's start on 215. In the second paragraph where it says remember. You guys there? All right. It says remember that this equation, talking about the ideal gas law, describes the behavior of a hypothetical gas consisting of volumeless entities that do not interact with each other. In contrast, a real gas does consist of atoms or molecules that have a finite volume. Therefore, the volume available to a given particle in a real gas is less than the volume of the container because gas particles themselves take up some of the space. Does that make sense? Okay. To account for this discrepancy, van der Waals represented the actual volume as the volume of the container minus a correction factor for the volume of the molecules, NB. Okay, so what's NB? Where N is the number of moles of gas and B is an empirical constant, one determined by fitting the equation to experimental results. So what you're going to see is you're going to see two kind of experimental constants that we're going to see. One experimental constant used to correct volume, and one experimental constant used to correct pressure. Okay, and those are just, really they had to determine those experimentally for every gas, and they're probably sitting in that physics and chemistry handbook somewhere. I think you've got, flip the page, I think you've got, yeah, there they are. But we'll get to that. Okay? Thus, the volume actually available to a given gas molecule is given from the difference V minus NB. Well, it would make sense that you would want to have moles in that correction factor, right? Because volume has a lot to do with how much stuff you have there. And if we're talking about gas particles do have a volume, we need to know how many gas particles there are, correct? That would make sense. Okay? And B is an experimentally determined constant. We're not going to go into, okay, how did he come up with these experimentally determined constants? Honestly, I don't know. And it really doesn't spark my desire that much to figure out exactly how they did that. I get the theoretical construct here. Okay? So what we're going to do here We're going to start putting this in. And we are going to, instead of just have V, we're going to have V minus NB. Following so far? If you don't want to put each step in, you're fine. We'll get it all put in at the end. I just wanted to make sure that you're following so far. All right, continuing on. The volume of the gas particles has now been taken into account. Right? The next step is to allow for the interactions to occur. Because we know that they do interact, they do attract due to the intermolecular forces that each gas has, correct? We can go back and review intermolecular forces of solids are held really closely together simply because solids have very low what? Energy, right? Guys, when a particle goes from a solid liquid to a gas, the intermolecular forces do not change. Does that make sense? The charges that the that the particles have does not waver. The only thing that changes is the amount of energy, or the energy affects how much those interactions do anything, right? Like we said, as we continue to add energy, those intermolecular forces are not going to be able to hold them as closely or as tightly. Low energy, particles can be held close and tight. More energy starts breaking those intermolecular forces, and when it gets to a gas, it's completely broken away. Make sense? Okay, just a little review there. All right. Okay, next step is to allow for gas particle interactions. Okay. The effect of these interactions is to make the observed pressure smaller than it would be if the gas particles did not interact. So what they're saying here is that having at high temperatures makes particle interaction, having it at low temperatures, makes particle interactions no longer negligible, and what does it affect? Pressure. Why? Why would particle interactions, the fact that particles can actually interact, why does that affect the pressure?
How often it hits the center of the container.
Yeah. So if gas particles are just going in a straight line, okay, they're going to hit the walls of the container and exert pressure, right? Well, now let's say gas particles are going by each other in a straight line, but they attract each other and they start to curve. Isn't that going to slightly change the amount of collisions that those gas particles are going to have with the container? Is it a lot of change? No. Right? But the fastest way to get from point A to point B is a what? A straight line. Okay, so if you have curved motion, you're going to have slightly less interactions or collisions with the walls of the container. Therefore, what's going to happen to the pressure if we do have particle interactions? Okay, here one says up, one says down. It would decrease. Because remember, fastest way from point A to point B is a straight line. So you would have more collisions if they were just going in straight lines, correct? And if they were curving, you would have slightly less collisions. Less collisions over time is going to mean less pressure. Okay? So let's keep going here. This effect can be understood using the following model. When gas particles come close together, attractive forces occur, which cause the particles to hit the wall very slightly less often than they would in the absence of these interactions. The size of the correction factor depends upon the concentration of the gas molecules, defined in terms of moles per liter, N divided by V. The higher the concentration, the more likely a pair of gas particles will be close enough to interact with each other. Does that statement make sense? What's that statement saying? If you were to abbreviate that.
The higher the charge, the closer the particles are, the more likely you're going
Say that again.
to. The lower the temperature.
Well, I didn't say anything about temperature, did I?
Which higher pressure?
What was that? Not bond, we're not talking
They're
bonding
collide.
here. Yeah, well, not collide, but like interacting, right? Okay, guys, this should make sense, right? More stuff, more interactions. right? If we had a bunch of kids in here, it's likely we're gonna run into each other every now and then, right? But if it's just 6 of us, we probably can avoid each other quite easily, correct?
Yeah.
Now you guys experience that when you walk down the halls. Okay? Alright, the volume in this case isn't changing, it's just more stuff, more interactions, therefore a greater decrease in pressure. Okay, so you can see why they have to have really kind of a moles and volume aspect to this. So not only are we talking temperature affects the interactions, but the interactions cause pressure change. And the reason why the pressure changes is because you've got particles and volume. It's kind of a lot, isn't it?
So if there's more or more interaction, the pressure goes down.
Well, then it would, right? Because if I have more stuff, pressure by scale would be greater, right? But the correction factor would be greater, and so it would be a little less. Does that make sense? So it's not, guys, if I have like 20 molecules versus 50 molecules, we're just going to exert more pressure. 50 by far, okay? But the 50 molecule one is going to have a bigger difference in the correction factor than the 20 would, because you'd have more interactions, and therefore the correction factor that we would have to apply to make that pressure a little lower is going to be bigger than if I had 20. Does that make sense?
It's exponential, not linear.
Yeah, it's like
Sure, you can look at it that way. But like, for example, right, 20 liters is going to exert much more pressure than something with, not 20 liters. Why am I doing
50
volume?
liters will be more.
We should have, assuming you have more particles with this volume, does that make sense?
Yeah.
Okay? Would exert more pressure, just because there's more particles there. Okay? Actually, I shouldn't do that. I should say both 20 liters.
Yes.
And then this just has more particles.
Yeah.
Okay? More particles in the same volume is going to mean more pressure. Okay? Less particles, less pressure. Okay, but what I'm stating here is how much we have to correct of that pressure. Does that make sense? Okay, what I'm saying here is there's going to be more pressure correction with this than with this. Why? Means I'm going to have to take a little bit more of this pressure and remove it than I would of that pressure.
There's more particles, so they hit each other more. And
More particles means that there's going to be more curved motion, if you will, right? There's going to be less straight line motion because it's a more cluttered environment. Make sense? What that's going to do is it means I'm going to have to, this pressure here is going to have to be adjusted more than this pressure. Does that make sense? Okay, and the reason why is because we got more particles. Guys, if I take this pressure and subtract a slightly more modification and take this and it's less that I'm subtracting, this is still going to be the bigger number after you correct it. Okay, it's still going to be the bigger number. We're just talking about how much we would have to correct. Okay?
Didn't you just say the last question?
What did I do?
You just said more particles is last question.
You're right. less pressure is removed.
less than you'd expect. Less than.
Yes. I'm confusing you, aren't I?
It's not the full 2.5 times the amount. If that's 50 and 20. It's not.
Yeah. So let's say this has twice the amount of particles. This isn't going to have twice the pressure.
A little under.
Little under twice the pressure.
So it's still a greater pressure.
Yeah, it's still a greater pressure. This still by far has the greater pressure, but the correction factor for that's going to be greater. Okay? All right. Where was I? Okay. So we just got talking about the higher the concentration. All right. For a large number of particles, the number of interaction pairs of particles depend on the square of the number of particles, and thus the square of the concentration. And here, this gets kind of confusing, but bear with me here. This can be justified as follows. In a gas sample containing n particles, just the number of particles, there are n minus 1 partners available for it to interact with. So everybody but itself it can interact with. Does that make sense? Okay?
Isn't that in moles though?
Yeah, but moles is the number of particles.
Yeah, but. Never mind.
Okay? Since 1 to 2 pair is the same as the 2 to 1 pair, this analysis counts each pair twice. Thus, the n particles, there are n times n minus 1 divided by 2. So it's saying a 1 to 2 interaction is the same as a 2 to 1 interaction. Does that make sense?
Oh.
Okay, so they're trying to get rid of doubling having each interaction twice. Okay, so that's what they're adjusting with the divided by 2 there. Okay? If n is a very large number, n minus 1 approximately equals n, giving n squared divided by 2 possible pairs. Thus, the pressure correlated for the interactions of the particles has that form. So, observed pressure would be your real gas pressure, not your ideal. You're not assuming that there's no particle interactions. Okay? How we do that would be our ideal pressure, what we would figure out in our ideal gas law, right? But we said that the actual pressure is going to be greater or less than our ideal pressure? Less, right? Because our ideal pressure is assuming everything's in a straight line, and therefore you would have a higher amount of pressure. So it would be your ideal, taking into account a correction factor. A is an experimentally determined constant, and then we said n divided by v squared. Okay, no, I'm going to put it all together. Can I do that for you? Then we're done. Can be. Sure.
I told that has to be, so it has to be where I did it.
Okay, so here it is. Here's your final equation. You have a spot in your notes for the Van der Waals equation? They write a little blank.
Yeah, you did.
So I'm just going to take I'm going to take this and bring it over so that I can adjust it for the observed pressure. So we'll say E observed plus A n over V squared times V minus NV equals nRT. I'm going to put this in brackets. What was that? That's his equation. So this is your corrected pressure. This is your corrected volume. What was that? A and B are constants. And you'll find that on the next page. You flip the page, there's a table in there that has the constants, experimentally determined constants for a variety of gases.
So it'll give us those numbers?
Yeah.
Will the problem give it, or we have to find it in the chart?
I don't know. If he doesn't give it to you, you have to find the chart. But like on a test for the quiz, I give it to you. Okay? So just remember that the corrected pressure is needed under what conditions? I know, but what was the situation that would have to make us high pressure? High pressure. It has nothing to do with pressure.
Low.
Because low temperature means that particles interact. Means that particles interact, and if particles interact, they are going to not go in a straight line, and if they're not going to go in a straight line, they're not going to hit the walls as much, and therefore you've got less what? Pressure. And then the volume is corrected because of under what conditions? High. Now I know it's kind of goofy to think that we correct volume because of pressure, and we correct pressure because of temperature. You see what I'm saying? It's a little difficult. Okay? You may leave. Take in
Yes, they're now.
What? No. Sorry, I'm not mad.